Steam turbines are powerful machines capable of withstanding thousands of pounds of pressure at temperatures as high as 1100 degrees Fahrenheit. Now, to the layman, a monstrous machine like this seems virtually indestructible. But to the knowledgeable operator, the turbine is easily the most delicate and precise instrument in the power plant. The function of the turbine is to convert energy stored in steam to mechanical energy used to turn a generator. Now, thousands of people depend on you, the operator, for the power to run their schools, businesses, and homes. Now, to do this, you'll be operating steam turbines. This unit will give you important information so that you can effectively meet this challenge. And we'll be answering some basic questions about turbines and turbine operation. We'll look at how a typical turbine is constructed, and then we'll cover the gland seal and gland seal exhaust systems. And next we'll see how lubrication systems keep things running. And finally, we'll give you some important information about how to operate turbines properly. Let's begin by familiarizing ourselves with the various components of a typical turbine unit. Now, during this presentation, we'll be using the most common names for describing turbine parts. Now, keep in mind, however, that your plant may use different designations depending on the manufacturer of your units. Ask your instructor to clear up any problems as to designations used in your plant. Now, here you see a simplified diagram of a typical steam turbine. Turbines are composed of moving parts, stationary parts, and systems of pipes and valves. We'll start with the moving parts: the shaft, the wheels, and the moving blades. The turbine shaft runs the entire length of the turbine and is connected to the generator. Turbine wheels are connected to the shaft and hold the moving blades, or buckets as they're sometimes called. Now notice that the moving wheels increase in size. This is necessary to get as much work as possible out of the steam and to accommodate the expanding steam as it flows to the turbine. The shaft, the wheels, and the blades are collectively called the rotor. The rotor is supported at each end by bearings and is housed in a casing called the turbine cylinder. Mounted to the turbine cylinder are diaphragms. The cylinder and diaphragms make up the stationary parts of the turbine unit. Diaphragms, as this drawing illustrates, are similar to wheels in that they're round and contain blades, or in some cases, nozzles. The distinction is made by the way they function during operation. As this end view shows, diaphragms are stationary and their nozzles are fixed in position. Their function is to direct the flow of steam leaving one set of rotating blades into the next set of rotating blades. Wheels, on the other hand, are moving parts. They're designed to turn as the steam flows through them. The rotation of the wheels turns the shaft and the generator. Diaphragms are sealed where the shaft passes through them to minimize steam leaking through this opening and bypassing the blades. They're positioned in the cylinder to separate the moving wheels from each other. This pairing of one diaphragm and one or occasionally two wheels is called a stage. Now, typically, a unit may have anywhere from 8 to 25 stages. Notice that our example shows 8 stages, but only 7 interstage diaphragms. Now, this is because there is usually a special type of diaphragm called either a nozzle block or nozzle box located before the first row of rotating blades. And as its name implies, this diaphragm houses a series of nozzles instead of stationary blades, which direct the steam from the steam inlet to the moving blades of the first wheel. Steam proceeds through the remaining stages of the unit until it's exhausted into the condenser. Now, before steam can enter the turbine through the steam inlet, it must pass through 2 types of valves: stop valves and control valves. Stop valves, alternately called throttle valves, remain fully open during turbine operation. The principal function of stop valves is to shut off steam supplied to the unit during shutdown or under emergency conditions. Control valves are used to regulate the amount of steam flowing to the turbine. Now, for this reason, control valves are sometimes called governor valves. Under normal conditions, the control valves are partially open to regulate steam flow during operation. Depending on the turbine design, steam may flow from the stop valves to the control valves through a system of pipes, as you see here, or through a large area designed to hold steam called a steam chest. Well, now that you have an understanding of the principal elements of a turbine unit, let's look at how rotation occurs. And we said earlier that the function of the turbine is to convert heat and pressure energy stored in steam into mechanical energy used to turn an electrical generator. This conversion is achieved by impulse, reaction, or most commonly by a combination of both. While the end result is the same, the method of producing the result is quite different. Impulse turbines work in a similar manner to this child's pinwheel. Air traveling in one direction strikes the pinwheel blades and pushes them out of the way, causing the wheel to turn, like this. In an impulse turbine, a similar thing happens. Now here you see the blade configuration of an impulse turbine. Here are the moving blades. Here are the stationary blades. As high-pressure steam is forced through the nozzles or through the stationary blades of the diaphragm, it speeds up. Then it strikes the moving blades, causing the blades and shaft to rotate. Now, since the moving blades are attached to the shaft also rotates. Reaction works differently. Expansion of steam causes the moving blades to turn. Now, this is easily understood if we look at a rocket engine. Here you see the tailpiece of a rocket. Burn fuel is exhausted through the narrow area of the throat. The exhaust expands in the wider areas of the tailpiece, creating a kick or force which propels the rocket through the air. In a reaction turbine, the moving blades act like the narrow throat. Steam passes through the moving blades and expands, causing the kick which turns the turbine shaft. As we said earlier, most modern turbines combine the use of impulse and reaction to make the most efficient use of the energy in steam. It is the designer's job to determine whether a turbine should be of impulse, reaction, or a combination of the two. Now, most large turbines are almost pure impulse in the first stage, almost pure reaction in the last stage, and a combination of the two in between. Now, you won't be designing turbines, but understanding what's going on inside of them will make you a better operator. So far, we've been talking about a simplified turbine. Most large turbines are divided into sections, and each section is connected to a common shaft. In this example, there are three separate turbine sections. A high-pressure section, which we abbreviated as HP, an intermediate pressure section, IP, and a low-pressure section, LP. At times, the different sections are referred to as separate turbines, HP turbine, IP turbine, and so forth. But operationally, they'll all make up one turbine. In another turbine design, the sections are connected to different shafts. In this example, the HP and LP section are on one shaft, and the IP section is on another shaft. This arrangement is called cross-compounding. Now, while each section in both types of turbines we've mentioned works in the way we've just described, they are not totally identical. For example, the wheels, diaphragms, and blades of each turbine section get larger as we move from high to low pressure. By the time steam has traveled this distance, its volume may increase as much as 150 times. Two things help accommodate the expanding steam. First, the size of the turbine is increased. Second, some of the steam is removed from the turbine by the extraction steam system. The extraction steam is sent to the feed water heaters, where it gives up its heat to the feed water. The steam in the turbine also gives up its heat as it passes from one stage to the next. Now, for this reason, it's often necessary to return steam to the boiler for reheating before allowing it to pass through the next turbine section. This most often occurs between the high pressure and the intermediate pressure sections. Reheated steam is returned to the turbine through another set of valves, the reheat stop valves and the intercept valves. Additional protection of the turbine is provided by these valves. As you know, turbine speed is regulated by the control valves. If turbine speed increases, the turbine control valves compensate by closing. Under certain unusual conditions, the turbine may begin to overspeed. That is, the turbine is turning at a rate much higher than it was designed to handle. An immediate danger exists that the turbine speed will increase to a point that centrifugal force will break it apart. This is where the reheat stop valves and intercept valves provide additional protection to the turbine unit. Now, if the turbine begins to speed up, the control valves will compensate by closing. However, a great deal of steam remains in the reheater of the boiler. The steam will continue to flow through the turbine, causing it to speed up. To prevent overspeeding, the intercept valves close, cutting off steam from the reheater. Now, if for some reason the speed continues to increase, the turbine trips. This means that all four valves, the stop valves, the control valves, the reheat stop valves, and the intercept valves quickly close, cutting off all steam to the unit. A trip protects the turbine from danger by immediately shutting it down. Well, we've now covered turbine construction and how the construction allows the turbine to produce power.